So as long as we're comfortable with the derivative of a function, and for right now, it's a new function that we get by calculating the limit of the difference quotient. We can do that. It takes a little bit of time, but we can do that. Once we're okay with the idea of the derivative of a function being a new function, this lets us talk about tangent lines in a different way. So I would say that if I have a function, maybe y equals f of x, and I have a particular coordinate on that graph, x coordinate a, y coordinate f of a, then the tangent line to that graph running through that point, well, it's the line that runs through the coordinate a comma f of a, its slope must be equal to f prime of a, again, the derivative of a. So I can always find the formula for this tangent line using the point slope form for linear functions. Here on the left, I have y minus f of a. Here on the right, that is equal to f prime of a times quantity x minus a. But let's think about what this means in the picture. Let's use some geometric reasoning. So let's think about this in terms of rates of change. When I'm setting y equal to f of x, I'm saying that y is a dependent variable. Whatever number x represents, that imposes conditions on y. So here we have, oh, those are my delta x's and my delta y's again. So we're using the Greek letter capital delta x to mean the change in x. And capital delta y is the change in y. So if x is going from x1 to x2, their difference is delta x. And that means that f of x2 and f of x1 are my two different y coordinates. So the difference of those is what I'll call delta y. And here they are on the picture. So my difference quotient, there it is again, is the ratio between delta y and delta x. It's that fraction. So this is geometrically a slope formula, but it's the slope of that blue secant line. So this would be my average rate of change. As I take the limit of delta x going to 0, right, this is playing the role of my h from the previous slide. My average rate of change gets more and more accurate to the here and now, what I would call instantaneous rate of change. So this is the kind of formula where I really want to say my dy divided by my dx, but differentials don't really exist in a way that I can perform algebra on them. So I have to go through the world of limits in order to actually get numerical results for this idea. So what the derivative is measuring for any function is the instantaneous rate of change in the variable y relative to change in the dependent variable x. So whatever our application is, if I'm measuring the instantaneous change in position, we usually call that velocity. Or if I'm looking at change in other quantities, we'll have other names for those things. How much is my bank account changing over time? How much is the energy in a chemical system changing over time? Well, with the tool of a derivative, we can calculate that with derivatives and with limits.